somebody wants to show us the categorical update on the profunctor Cosmos and so on.
I could show it, I guess.
Your beautiful diagrams. Your
I
handwritten.
don't have any diagrams now.
Ah,
I thought I was trying to see what I would diagram, but I don't understand it well enough. So.
I have one
Yeah.
diagram which I can do after this, but it's not pretty, but I did find it helpful. So.
Oh, you want to do that first? Let's do that first.
Sure.
Okay, let me stop share.
a picture is worth 1,000 words.
Yeah. Yeah. Let me put it in the right place first. So yeah, I've just been trying to understand, I guess, ends and coends, specifically coends, because that's what shows up in the paper. So you can probably see my browser here.
Yeah.
Yep, we can see it.
Cool. So this is my ugly diagram, which is done with like LaTeX tables.
Uh-huh.
my curved arrow there. Yeah.
Can you make it bigger, maybe?
Almost
Change your screen to more horizontal. Or maybe it's my problem. Make this
Yeah.
bigger.
Command plus again, maybe one more time. Yep.
Is that helping?
Yeah.
Good. And we also probably want to, let's see, get rid of some of the cruft there. Is that, y'all see that fairly well?
Mm-hmm.
Good enough.
So what are you using there? Is that LaTeX or
This is
something?
MathJax.
Oh, okay.
The thing that
Yeah, I
they
know.
use in like math Stack Overflow or Stack Exchange Math or whatever it is.
Right.
Where you just like type stuff in and
I
so
see.
the idea is
Okay.
that if I need to adjust something here, if I make a mistake, I can actually go up here, change the source code, and yeah.
It'll update. Yeah.
Yeah. Just in case. Anyway, so this is more or less my attempt to understand the definitions in NLab. And a lot of people have said this stuff already, but it just kind of puts it together.
Let's say it
So,
again.
so you have a functor of this form, like this bifunctor thing here. And you want to define a coend of it, which is a bunch of arrows from f of cc to your this object, which is going to be the coend. And it has to set us. So this is a definition that actually works, and which I can almost use to try to prove things, at least to a limited extent. So first of all, this object has to be a co-wedge.
Mm-hmm.
Means that for any arrow phi from C to C prime, you get this extra natural square, which has to commute. So that's the first condition, and the second condition is that the coend must be initial with this property. So
What is extra natural?
It's let's see. So if you have something of this form where you have a whole bunch of maps, sorry, a whole bunch of arrows from f of cc to some object, then see this square looks a lot like the square for a natural transformation, but it's different. And specifically, it's different because the maps that you want to say are extra natural actually occur, they're like both on the same side, as it were. Normally, if you had a natural transformation, you would have one of your maps on one side and one of them on the other side. You know what I mean?
Mm-hmm.
Yeah. But anyway, there's this concept of extra natural where it's on a functor, which is it applies to a functor not from one category to another, but a functor which is contravariant and covariant in this on the same category. Anyway, it
True
doesn't matter.
functor, a
just-
true functor, actually.
Profunctor, yes, that's right. I guess it's the same as the shift from functor to profunctor. which we're
So
still
this
having
is
some
this
trouble
is
understanding.
this is a kind of analog of naturality for proof functors, right?
Yes.
And the interesting thing about it is that you have to begin on the left upper corner of this diagram with f of c prime c. And not as, so you have to begin with this weird f of c prime c, because you have to, you can map this into FCC by mapping the first argument, c prime to c, because it's contravariant.
Mhm.
And you can map it to f of c prime by using this covariant in the second argument. So that's, and then you can use this arrow IC and IC prime on each of them to arrive to the same result.
Mm-hmm.
As far as I can say.
Yep.
And so
So that is also called the co-wedge condition. They usually start out by doing the end definition, and that has wedges. This is co-ends and co-wedges, which I hope is not too confusing. But anyway, so this is also the same. This commuting square is the same as the co-wedge condition on the maps. Out of C. Sorry, Sergey, you were saying.
no, I'm just saying what we have seen before, but probably already forgot, is the dinatural transformations. And this is relevant. This is quite similar, except that here we have an IC, which goes from f of CC into some constant object that does not actually depend on C. Right, so the coend does not actually depend on C. And it is a little C in it, but it's confusing. The coend does not actually depend on the object C.
It's a bound.
C.
Yeah, it's a bound variable, basically.
I mean,
Yeah,
shouldn't there be an argument? Shouldn't there be a term after the integral sign if we?
Yeah, capital F maybe.
Yeah, something like that. Yeah.
Capital
okay.
F and then
It would
C,
be like
comma
f
C.
of CC.
That's right.
Yeah,
Yes.
you're right.
Integral of C FCC. That's right. That's right. That's more
Okay.
clear than, yeah. So it's not actually, it does not actually depend on the objects on the left.
Better.
Yeah.
Yeah, well, so since it is a bound variable, it could have been integral of x f of x for some reason,
Right.
for example, right? So it does not have the same C
Right.
as the things on the left.
Mhm.
So
Maybe T.
yeah. So anyway, so what I was going to say is that if you have a transformation between two
Should be
profunctors,
X because it wants to be a variable.
Already got an X though.
that doesn't matter.
Yeah,
Okay.
That's good enough.
T is
Yeah,
not a variable.
that's good enough.
excellent.
So, right. So this, if you have, imagine that you have two profunctors, f and g, and you have a transformation f of cc into g of cc. So then the naturality law for that kind of thing is it has a similar form. Right here, you can somewhere see.
No,
No,
it's the
no.
hexagon.
It's the hexagon. Yeah. Do you
Yeah,
see the hexagon somewhere? Yeah,
there it is.
it's right
Yep.
here. Yep. That's right. So this is the hexagon when you have PAA to QAA. Now,
Mhm.
what we have is a QAA that doesn't actually depend on A.
Mhm.
So instead of PAA, we have F of CC, right? But instead of QAA, we just have a fixed object that doesn't depend on A anymore.
Right. So the two
Yeah, so these two could just
collapse into
collapse.
one.
They
This
just
whole
collapse.
thing sort of collapses into one,
Exactly. Yeah.
Yep.
node.
So that's why it looks a bit different from naturality, but actually it is quite analogous. It's just that by chance we can simplify this. This hexagonal diagram would have been there, which is dinaturality,
Mhm.
and but because Q is trivial in its argument, QAA is the same as QBB, and we don't need this lower part of the hexagon at all. So we can just collapse it into one point.
Mhm.
So it ends up being a diamond, huh?
It ends up just being a diamond, but actually it
Yeah.
is just a kind of
A square.
analog. It's really a hexagon
Mhm.
with collapsed end, and with some collapsed parts. And this is really analogous to natural transformations and naturality law, except that you have profunctors. So this is the analog of naturality square, but for profunctors.
Yeah, and he mentions that you can actually, since a profunctor is in particular a functor, you can
Yeah.
also require that something be a natural transformation on that functor on the product category, but that is strictly stronger, he says.
Yeah, that is stronger. Yeah.
But I know
Is-
that, yeah, I know there's a, from reading his page here, it appears that profunctors generalize functors and ends generalize limits. And I see that the flavor is similar, but I don't see, it's not clear to me that one generalizes the other in either case. So that's still kind of foggy for me.
Well, I can't comment on that.
Anyway, well, let me just finish this this brouhaha. So this has to be satisfied, and that makes the integral together with these I maps. That whole thing is a co-wedge, right? That's what it says for this to commute for all phi.
Okay.
But if it's going to be the co-end, it has to be the initial co-wedge. So if you have another one X with maps J, such that the similar, I guess the outside of this whole thing commutes, then there's a unique arrow in here, which makes the triangles commute. That makes sense?
You say makes the triangles commute, but
Yeah,
they look
so-
kind of still like rectangles. Or
There's a triangle here and there's a triangle here because
What are you using to draw the diagram?
these are LaTeX tables.
Oh,
So this thing with the ampersands and the,
okay, so that's okay.
it's,
So then
it's not,
yeah, okay.
not
I
great,
see.
but
You cannot draw arbitrary arrows in this way.
oh, no, can't do that. So there's an arrow JC prime that goes from here to here, and there's an arrow JC that goes from here to here. So these are curved arrows coming around here, which means there's a triangle right there and a triangle right there. Basically, the reason I found this diagram helpful was it looks exactly like, you know, what we did for, you know, defining pushouts or co-limits of whatever kind. It's very similar.
Yeah. Okay.
And that also tends to clarify something that I read in the NLab, which is they said, oh, if you want to construct this coend, it's basically a coproduct modded out by an appropriate equivalence relation. And that actually looks pretty clear to me from this diagram. So it's a coproduct of all of the FCCs, except that you also have to make it a co-wedge. So it has to satisfy this.
I would like to understand this modding out business.
Yeah.
So how do you mod out? So you have a product of coproduct of FCC, right?
Yeah, so FCC, so again, here I'm just going to say that X is set, which probably it is, right? Certainly for Miliuski it is.
Yeah.
So say it's set or something, that's, yeah, let's just say it is. So if we can take the coproduct of all of the FCCs, right? It's just a bunch of sets. We can take the coproduct.
Yes.
And we can then, that'll have the universal property, okay, right? Because it's a coproduct, but it won't in general be a co-wedge. The square will not be commuting. But we can just force the square to commute by saying, okay, you have this coproduct, and now I want to mod out by a bunch of stuff. So anytime you have one of these squares, and you have an element here, which maps into this FCC prime, and it also maps into this FCC, they have to be the same. Right? We want to force them to be the same. So that means we say, okay, anytime that happens.
So, okay, so wait, what exactly is the same and how you mod out? So when you say I have a coproduct over FCC, then when you so the arrows I see are just injections into the coproduct.
Yep.
So then you're saying that in this coproduct, some of the parts are forced to be identical. So for example,
yes.
I find some value of from f of cc.
Yeah, f of cc is a set, right? So it has an element.
Yeah, I found some element which is f of c prime c, and generate from it two other elements, f of cc and f of c prime c prime.
Well, wait, you don't. These are in the diagram. These things are sets, and the things we're identifying are going to be elements of those sets.
Right. So I start from an element of the set f of c prime c on the left upper corner. It's an element which I map into an element of FCC down. And I also map it into another element of FC prime C prime over there. So then I say that these elements must be injected into the same value. But,
so they do inject into the coproduct, right?
But they will be in completely different parts of the coproduct.
Yes.
The types the C prime and C are different. So what does it mean that you identify them? They're very different part of the coproduct.
Yes, but the coproduct is just a set, right? If you have an equivalence relation on a set, you can mod out by that equivalence relation. So you just have to say, what is the equivalence relation exactly?
I see.
And it is the smallest equivalence relation, which makes all of these things true. It's the equivalence relation generated by all of these. And here I see that I already used the variable t, which I'm now using in two different ways anyway. But yeah, and we did something similar to show that, this was a while back, to show that like limits should always exist in set. In that case, it was, well, let's say colimit should always exist in set. You can just take the coproduct and mod out by like the thing that will make your cones, make everything into appropriate cones. Your cones have to be correct. Your cone triangles all have to commute. So you mod out by what you need for that.
Yeah.
And then you're done, because you have the fact that you mod it out by that means that all of these squares will commute. And the fact that you started out with a co-product means that this thing will be initial with that property. You will always get this unique.
So I'm a little confused about your equivalence there. How do you apply F to T? F of like something, something. I mean, isn't that just
Oh,
set?
you're right. Yes. So after the, oh no, okay. So
No,
F
that is
of one,
notation. That is just notation.
yeah,
Oh,
F-
I see, because that's actually a function. You're using it in the functorial sense. Okay, never mind.
yeah. So yeah, so one C prime comma phi is a
It's the function. It's a
Function from
it's
FC,
an
FC
arrow
primes.
in this category, and that means you can apply your functor to it.
Okay, and that gets you the arrow in that.
That gets you an
Okay.
arrow in sets, right? And you can apply that arrow to this T
Things
or
in there. Okay, got it.
That makes sense.
Yeah, the
Anyway, I was
notation.
hoping to go on from this and say, because I still would like to know, I mean, I'd like to have a good example of this. So there is an obvious example for F, right, which is hom. So what is the coend of hom? And I've been trying to do this as an example, and I understand some things about it, but I still don't have an answer. So if anyone else knows this, maybe you could let me know. I think Miliuski was talking about something similar, but not the same.
Wouldn't it be all the arrows of the category?
I don't know.
This is very interesting.
Anyway, if I make progress on that, I will present it to you.
I would
But-
rather try to make an example that is relevant to programming, because then at least you have some intuition about what coend is doing. And then the coend is the existential quantifier with some parametricity constraints. And then we have an co-UNIDA lemma that tells us what that existential quantifier should do applied to certain profunctors. So we know what the answer must be. And so then we can try to understand if we can reproduce that answer through this construction.
Yeah, and I guess Miliuski is getting closer to that because he's talking about actual types and theoretically programs and so on. But this at least gives me some intuition for how you might try to build a coend, or at least it will help me remember the definition.
Well, to me, it's a very difficult construction because you have a huge co-product and then you're modding it out by an identity relation that's parameterized by C, C prime, and phi.
Yes.
So, and T also. For any T, so you have a very large number of identifications to make. It's not
Actually,
obvious.
Go ahead, sorry.
I stop. Yeah. All I'm saying is that it's not obvious how you can write down the result of all those identifications.
Yep. And actually, there's another thing that I fudged, which is that C here is ranging over all sets. So this thing is actually larger than a set. We have set theory problems now. This thing is a proper class, I think. So I'm just sweeping that under the rug for the moment. But again, for programs, I don't think that'll be.
For all sets.
Anyway, that was my rendering of NLab into something that I understand better.
Well, this is really more clear, yes.
Cool.
So, yeah, okay.
No, please. Anything else?
Just as a meta comment, there's a LaTeX package, TIKZ-CD, that's like good for drawing commutative diagrams.
Cool.
So
Yeah.
I don't know if
Yeah,
you
this,
could use it in that tool, but
I don't think so.
I actually haven't used it, but I've seen other people use it, and it's pretty easy to use.
That's great. Yeah, no, I think probably rather than use, the sandbox in someone else's website, I should just make my own text document and process it right here, and that would do better.
You should
So,
start
yes.
writing your book.
Yeah, right. My yes, my own magnum opus.
Yeah, what? I mean, then you have all the explanations, and they stay.
Yeah, well, I'll keep this around. Maybe that'll help.
So yeah, so as far as I remember, then the ends are defined also in a similar way. But anyway, what is
Yeah, but what finally helped my intuition is to think of an end as an infinite product, and then kind of a sub-object of that infinite product. And then the co-end then is an infinite sum, but again, as Hugh said, to mod it out in a suitable way. So I think the notation of using integrals for both, I think, was a mistake, because the sum makes sense, but the product, the end, does not make sense. So to me, it's misleading to think of it as an integral, whereas co-product is definitely an integral with some overlap of the individual elements. But anyways, that's what finally clicked for me. And then the concrete example of the natural transformations as an example of an end, that was
right.
good.
Yeah, that's in NLab. It's also in Miluski.
He mentions that it's kind of like,
go.
instead of modding, it's like an equalizer. So
right.
Yeah, you can also look at it as an equalizer, which I didn't go into that, but yeah.
Okay.
I guess yeah, so equalizer is a subset, right? It's the subset on which things are equal. But the co-equalizer is a quotient, because it's the
so duality. This is sort of like you're forcing all your paths to end up sort of being the same thing. Yeah.
So okay, yeah. So this is interesting. So when you write for all A, FA to GA, and you impose naturality, then you get the end of the profunctor. And when you write exists A and then some profunctor, what do you impose? If you again impose parametricity, is that sufficient? Because he writes, the reason it works in Haskell is because naturality follows from parametricity. So in other words, you say, for all A, FA to GA are not just any functions, but those that work in the same way for every A. So they're fully parametric in A. They can only use code that is independent of specific type A. So, and as long as you use that code only, which is pretty limiting, of course, but that's the price. As long as you use that code, then your function automatically satisfies the naturality law. And so then this for all A is actually implying, because Haskell does not allow you to do non-parametric code, but Scala does. So then you have to check, but I'm curious what happens with coends. So, because does it also just magically work in Haskell because of some stuff? Or do we have to squint harder? because coends, you know, you've got exists a PAA, right? Quotient, and then pseudo Haskell exists XPXX to C. The sum type is replaced by coend, and family of handlers becomes an end. I see. So he's just using Haskell code for end, because there's no Haskell keyword for exists.
But that's, yeah, that equivalence is just sort of currying, right? In some sense, because
Yeah.
since X is not free in C, you can,
Well, this is
those two are the same, basically.
so they're the same, but the thing is, on the right, you have for all X, PXX to C. That actually implies parametricity. So PXX may not be arbitrary values of type PXX. There must be, so P is a profunctor, so it is contravariant in the first type, right? So it will contain some kind of function from X to X in some way. And these functions must be fully parametric in their type parameter. So this is implicit in Haskell. So you see, so on the right-hand side, we have some parametricity condition. But on the left-hand side, what do we have? Can we write that as a parametricity condition? Is that sufficient? So this I don't know. But in any case, you can just say, well, I never actually use coends, I only use ends. And then you're kind of fine with that. But that's not always the case. Sometimes you need code that has an existential quantifier. And then I would like to understand what is going on.
But if, let's see, if you can always just flip back and forth, then.
Well, you can't flip if you don't have this arrow. So he begins with the arrow, right?
This one?
From, yeah.
Oh, right.
But what if you don't have this arrow?
But when they use that notation above, that's, those are arrows. Those,
Yeah, but
right,
why do you
set
write them?
of two things.
Yeah, but why do you write that? I was not interested in that initially. We were interested in just the coend, right? Integral x pxx. We just wanted to understand what that is, not arrow from it to something else. What if you do not have this arrow? You're asking, you have code that has a value of this type, not an arrow, but just a value of this type.
Okay.
Right? How do you talk about that? Well, I would actually say, I know how I would talk about it. I would do a church encoding. I would do that to C and again to C. I'll put a quantifier in C in there. And that will give me maybe what I want, but that's actually not true. So no, I don't know how to do this. So what I'm saying is that yes, you can have this equivalence of arrows, but what if you don't have an arrow? What is then the type?
You're sort of saying, how do you think about the coend without like?
What are values of that type?
Yeah, right. So if someone gives you the profunctor,
yeah,
what is the coend of the profunctor? How would you describe it?
What are possible values of that type? What are possible elements of that set? How do you describe them? Not arrow from that to some C. but just that set itself.
Yeah, I
Well,
don't-
every element in that set is the element of some PCC.
Yeah.
Right.
Maybe, but there's these identifications that you're supposed
Yeah.
to
Right.
do.
It may be in multiple PCCs.
So I don't know how you implement those identifications.
So in the case of HOM, again, this is the example I've been working on, which may be a poor one to start with, but in the case of the HOM profunctor on set, an element of the coend would be some collection of like self maps of various sets. So like, which ones? That's what I've been.
Self maps.
Yeah, they're
Oh, because you're going down the diagonal.
yes, or it's, you know, whatever, PAA, right? It's well, actually,
So HOM AA is basically all
so-
the arrows from A to itself.
endomorphisms, actually, endomorphisms of sets.
Right.
That's what these things are.
Hmm.
Anyway.
Right.
So,
And then you're taking the union basically of all those things.
yeah,
But then there's some identification.
exactly. So if I could understand the identification better, then I would understand what's going on. But maybe there's a better example than HOM. Maybe there's like something smaller or more concrete. I didn't see anything like that in here. I mean, I didn't see a list of, okay, here's a profunctor and here, well, okay, I guess in the case of, we did do natural transformations, right? This is the one that you mentioned, Young Yo, where if you choose this to be your profunctor for some functors F and G, then the end is just a set of natural transformations between those functors. Is that right? I think that's right.
Right, because you can think of the natural transformation pi there as actually a function that takes an object and then returns, you know, an arrow. So that's why it's if you think of it as a so for each index A or B, you know, you have the set of arrows, and then you take the product of all of them. And so that is, so that what is an, and so that's the end. And then if you pick out one point in that product, right, then it's A coordinate gives you pi A, its B coordinate, you know, B component gives you pi B, and so on. So that's, you know, the infinite tuple is a point in that the set of natural transformations. So
yes, and the fact, well, you actually, it's not the entire product, right? It's the subset of the product, which actually makes this thing
makes the commute. Yes.
turns out to
right.
be exactly the naturality condition that you want for your natural transformation. So I wonder if this is a profunctor, then it could also have a coend, right?
You would think so. But yeah.
I wonder what that would be then. Maybe it's natural transformations in the other direction.
No, no, that would be too simple. No, because at
It
the
would be at
end
the
is
bottom of the diagram.
right.
Mhm.
So if the end is an infinite product of all the sets of arrows, then the coend would be an infinite sum of something.
Mhm.
Yeah.
You'd sort of have to flip this diagram, put the coend at the bottom with the pies going into it, except they're not projections. So I guess you use a different letter like I or something
Oh, I or iota. Yeah.
for injection. And then the CFAGB would be at the top. But
Mhm.
Maybe there's a good example there.
I don't know if that helps.
But presumably not all a profunctor is not guaranteed to have a coend, right? In general. And it's not guaranteed to have an end either.
Right.
Why not? Oh, because if it doesn't satisfy the condition.
Yeah, I mean, it's
Okay.
just by definition, it's a set of this data which
Yeah.
meets these criteria. So we don't know that there is one. In the case of the set here, I was arguing that this construction should work in the same way that we constructed limits and co-limits in the category of sets. So it should
Mhm.
work, although there's a set theory problem, but basically that same intuition of taking a subset of a product or a quotient of a coproduct should still work. But I don't know that that works like for every category. I'm pretty sure, surely it doesn't. Surely there are categories where that doesn't work at all. Anyway, we
Yeah,
wandered a
yeah.
little far from our paper, but I think this is all pretty interesting. He did say that ends generalize limits in some sense. Yes. End is a generalization of a limit. So does that mean we can regard any limit as an end?
Yes, in the sense that a functor is a specialization of a profunctor, right?
Okay,
Where
sorry. Can I pause you there? How does that work? Remind me.
You just fix the first component.
Yes. I mean, you just, make the first component a dummy.
Okay. So this is a profunctor to set, but it could be anything really.
But it's functorial in both arguments. So if you make P of D, just fix the first argument, then you're left
trivial?
with, what's that?
Do we make the entire category D trivial, for example?
Yes, that's one way of doing it.
Could work. Okay. Okay. Sorry. So you were saying, Young.
So in that sense, yes, a functor can be thought of as a simple profunctor where one of the arguments is fixed, a constant. So then the limit of a functor is like the limit of a diagram. So then, it is a generalization in its 2 dimensions. So, but maintaining the what is the condition we call it again? That hexagon.
This one.
Yeah, the dinatural. Yeah. So natural transformation becomes dinatural, and what I find kind of curious though is, excuse me, that the use of the diagonal, right, is key here, and that allows us to go from PAA into QAA, and then we go from the diagonal back into the off diagonal using the F. And so it's like there is a certain global constraint, right, that is imposed. So just like natural transformations are not just arbitrary, they have to apply to every single object in the source category. And then there has to be an arrow in the target category for every single object, which makes all the diagrams commute. And so it's a very, natural transformation is actually a very strong condition that you don't just find it anywhere, right?
It has to be uniform. In some sense.
Exactly.
Well, what you're saying by global, you mean there's a condition that relates these alpha A's for
Yes,
for different A's together. So
that's right.
you
That's
cannot
right.
you cannot arbitrarily select, P int into Q int, and P float into Q float,
Yeah.
and P string into Q string. Cannot arbitrarily select each of them separately. They must be coherent with each other. And so this hexagon is the analog of that kind of coherence,
Right.
where you only have proof functor P diagonally transformed into proof functor Q. You do not
Mhm.
have arbitrary PAB transformed into QAB.
Right.
That would be full naturality, and that is stronger. If you have
Right.
that kind of transformation, then you just need naturality squares separately for each type parameter. But you do not have that. You only have diagonal transformations. So,
Yeah, that second diagram is I think that is the naturality. If you
yeah,
had the naturality condition, that's what
yeah.
it would look like.
Well, that would look like if you had alpha BA. You see,
Mhm.
in the center of this diagram, you have alpha BA,
Right.
which means you're supposed to be able to transform PBA into QBA with arbitrary type parameters, not necessarily diagonal.
Mm,
And you usually don't have that. The whole point of using proof functors is that you use them diagonally
Mhm.
in your code. You have a type constructor which is neither covariant nor contravariant. And this
Mhm.
type constructor is a diagonally used proof functor. That's how you use them. And if you just have PBA into QBA, it means you have a type constructor with two type parameters, but they're used separately. You can have arbitrary first one, arbitrary second one, and you can transform PBA into QBA with. So you could, for example, transform PBA into PAA or PBA into QBA and then into QAA, whatever you want. You can. So you don't need special naturality laws for this case. You just have naturality laws separately in each type parameter, which he draws as this hexagon, but doesn't have to draw it like that. It's just that you have separate naturality laws for two type parameters. There are only two squares actually to be drawn. But the first hexagon cannot be simplified. And it's a very weird condition, actually. Because it's a condition between functions from PBA into QAB. And that has to be like this. There's no other way you can do it. And that's a pretty weird condition. And so I know this because I have used this in some places in my book to derive naturality laws. And what I found is that dinaturality is weaker than relational parametricity would give you. So it is a consequence of relational parametricity, but it's weaker.
mm,
So if you have a profunctor PAA going to profunctor QAA via parametric code, then you have actually a stronger condition on that function, which would be obtained through relational parametricity with arbitrary relation. And that is not equivalent to this hexagon. It is actually stronger than this hexagon. And how I found about it, at least at first, I thought this hexagon is great, and that's all I want. I will use it. It's very easy to write down. And then I found places where I could not prove what I needed to prove with just this hexagon. I just didn't have enough information from this hexagon. And this is because it has this PBA to QAB. How do you get the right value of type PBA? Why do you want that value? Maybe you don't have that value. So anyway, so what I'm saying is that, yes, so there is this dinaturality transformation, and it is a consequence of parametricity, just as naturality is a consequence of parametricity. But this does not replace the use of parametricity. When for natural transformations, it does. You don't need directly parametricity for those. But if you have a profunctor going to another profunctor, then you may not be good enough with just this hexagon. And for example, for the fold, you don't need, you need the full relational parametricity property and not just the hexagons. The hexagon is not good enough for the fold. And there are other places where it's not good enough. So I found at least 2 places where it's not strong enough.
So
But,
I noticed there was a, sorry, I don't know, there's a transition here, which I didn't notice immediately. A profunctor in general has 2 different categories in the domain, right?
Right.
But here, suddenly they're the same one.
why 2 different?
No, here.
Oh,
I mean, in general.
In category,
right?
yeah,
Yeah.
it could be different.
So is
Okay.
dinaturality specific to the case where those 2 categories are the same? I guess it must be.
yeah.
Okay.
Oh, really?
Yeah, well, because you have a function f, just one function f, which is an arrow in just one category. So if you have 2 different categories, you cannot use this thing. Because the same function f is used to go to the left and go to the right.
Yeah. Okay.
Yeah.
And also, what does it mean to have a diagonal if you have 2 different categories?
Yeah.
Right.
You can't have a diagonal.
Right.
So this entire thing just doesn't apply.
Cool.
Uh-huh.
And the diagonal concept does show up with limits and colimits, I remember too.
Right.
There's that the limit is the like the left adjoint of a diagonal functor or something like that.
Okay.
That seems important too, and that must be related to this sense of diagonal somehow. Let's see. I think they mention it here. Is somewhere in here. I would like to understand this. Yeah, so I mentioned this last time, as I would like to understand this statement too. Limits are right adjunct to a diagonal functor, and there's a right adjunct to a Helm functor. Anyway, that's probably just going to be a distraction now, but that diagonal thing seems to keep showing up as a concept.
What is the diagonal functor in their terminology?
Ah, yes. So let's see. Basically, so you have
Is it basically the functor from A to PAA?
and understand in terms of diagrams. Okay, so if you take the limit of a diagram, right, then someone gives you a diagram and you give them back an object, basically an object with a bunch of arrows on it. You can go the other way and say, if someone gives you an object, you can build a trivial diagram from it, which has the same shape, which has a given shape. So it's trivial. You put the same object into every node of the diagram, and you put identity arrows in for all of the arrows. That's the diagonal functor from the category, the ambient category to the category of diagrams. Does that make sense?
Okay.
And it's diagonal. I mean, you can see it most clearly if the the diagrams are just, let's say, pairs, right? They're just your shape of diagram is just two objects with no arrows between them. So the limits of that shape are just products. But if you look at the diagonal, it just takes an object to two copies of that object. So it's just the ordered pair of two of those. So diagonal sort of geometrically makes sense in that example. So yeah, anyway, I would have to fill in more details, but that's, I believe, what the diagonal functor is. It's that trivial functor. And then you can look at a limit as adjoint to that because it's going in the other direction.
Yeah, okay. I see. Right, so you can think of in the simplest case, a diagonal is a functor from the category that has two objects, 2 into, let's say, x, right? So basically it maps the first element, let's say 1 into something, and then 2 into something else. But the diagonal means that 1 gets mapped into the same object as 2 gets mapped into. Is that right? So basically, you have x comma x. In general, then, the exponent can be any diagram delta, and you can map delta. Each of the points in delta can be mapped into arbitrary objects, but the diagonal functor maps delta, where each of the points gets mapped into the same object, let's say x. So the shape of delta is made up of all the x's, same x's, with this identity arrow between all of them.
Yeah, the idea is right. But
Okay.
To be more precise, let's see. So I guess limits go from the category of diagrams to the plain old ambient category.
Yeah.
And I think the diagonal construction goes in the other direction. So if you just take an object of the diagonal category, it gives you trivially a diagram.
Right, right. And the diagram is a functor, and at each object, the functor maps you to that original object. Yeah.
Yeah.
Okay.
Makes sense. Yeah, I should like fill this in on my own. But okay, I'll try to clarify
Okay.
that for my own satisfaction. I think we're wondering a little bit. Although it is interesting, yes, and the reading about extranatural stuff, that was pretty funky as well. That also has to do with adjoint functors, as it turns out. Anyway. So did other folks look at this chapter of Miluski?
I
And
did.
how far did you get, and where did you get stuck? Or did you?
I didn't read the chapter, but I watched his YouTube video on.
Didn't read the book, but you watched the movie.
Yeah, I watched the movie, and I appreciated his YouTube video because he's talking about these things without any notes, and so he spends kind of like and then he's trying to figure out what the notation should be, and then he makes a mistake because he uses the same letter A and F, and then he realizes, oops, and then he switches it, and it kind of, he kind of throws out a lot of comments which really were more helpful than the text itself, I think. That thinking process I found fascinating, and I'm thinking to myself, wow, you don't need to be polished to help somebody to learn. That struggling that I see him doing on this video actually was very insightful.
It's helpful. Mm-hmm.
Because I'm struggling the same way. And then when he says, yeah, it's kind of like this. So.
It's interesting because I would usually find it frustrating if I don't understand and it makes no sense, and then it was A instead of B, and then I spent all this time trying to understand why there is an A, but now actually it's a B.
Okay.
So
I agree with you. Coming
I've
up
done a
with a
lot of
good-
this. I've done a lot of presentations where I had notes, and every time I tried to improvise, I ran into problems, severe problems. I have to, and then I just decided that it's hard, and most of the notes have to be done, and most of the notation has to be figured out. You can improvise a bit, but you cannot just go empty-handed with a technical presentation where you have X, Y, Z, A, and B. You always mix them up. And anyway, but
Yes.
to me, his lectures are just, a lot of chatting, a lot of ideas that are not clearly explained. His text is, in my view, better, and it's just that some of the places in this text should be explained even more. But anyway,
Yeah, that's
He's
what I
pretty
found.
good about, I imagine that sort of intuitions and heuristics might come out more clearly in a talk, even a rambling
Yes.
talk, than they would in text. But I think when someone does a good job with writing a text or an article or something, they throw in a bunch of the intuitions and the examples that are helpful.
oh, tutorial text should go through the intuitions.
Yeah.
It should not just say, definition, theorem. It should explain why you want this definition and why you don't want some other definition. It's just a lot more effort to write that than to talk.
Yes.
Yeah.
Yes.
A lot of times it's like, consider this definition. It has this property. It's like, oh my God, where did this definition come from?
Right.
Yeah.
One example, I mean, it just takes a lot of time to write it all down, and a lot of these calculations are hard and don't even like what Hugh was presenting. F of 1 C prime phi t. Even notation is confusing, and you have to keep all of this in your head, and it's just a few times Milevsky says, here's this diagram, convince yourself that it is commutative, and so
But even his writing, it gets confusing because one diagram he'll use alpha for the legs, and in the next diagram it's pi, and he uses alpha for something else. So it's like, be consistent.
It's hard. You try to be consistent, but then you edit the text, and then it becomes different, and then you have to edit again. It's a lot of work.
Yeah.
I mean, I have seen a lot of books papers where they draw a big diagram and just say, okay, here it is, it's commutative, done. Look at it and convince yourself that it is right. Now, how do I do that? What are the steps in the convincing? How do I write down these steps and check that they are correct? Did I convince myself because I just wanted to skip and go on, or because I know what is being done? And so he does some of this too. And this is just a lot of work, and people don't like. Recently, there was a book published with the title "The Book of Monads." A lot of monads explanations and all that, and then I was interested to see what is in that book. Can I learn something from that book? And by the way, it says Scala and Haskell kind of side by side. So okay, it formulates the laws of the monad and kind of explains where these laws come from, which is kind of good. Not a lot of people do this. It does not prove these laws for a single monad. not a single monad. So, okay, I mean, why did we formulate these laws? You know, we're not going to check them, right? And it is not automatic that they hold. It is not obvious that they hold. So not necessarily, they don't, you know, necessarily hold for arbitrary code, even if you have the right type signature. So the reason why they don't write the proofs is because it's long and hard, and you don't have the notation for the proofs to write them quicker, and it's a big mess. So my book spends at least 400 pages just on proofs. It's horrible. It's just.
Who's gonna read your book?
I don't know. I don't know. I mean, you know, I don't know. I want to write down the proof. It's not always obvious, and I haven't seen these proofs anywhere. Nobody proves this. I mean, we'll write down the state monad. The state monad has a type signature for the flat map function, for example, that you can implement in different ways. Only one of them will satisfy the laws. So do you know? Do you know that you have did it correctly?
Yeah.
There isn't any book or any paper where this is written out.
I wonder how many. I wonder how much code there is out there that claims something as a monad or a monoid or you know, applicative or something, which is even though it's actually false, because you can
That's
do
the
that
right signature, but it doesn't satisfy the laws. Huh?
Yeah, I mean, I don't know. I mean, usually you would, and
Sure.
there's one example where the list monad transformer was wrong in the Haskell library for like 5 years. It did not satisfy the laws, and well, they fixed it, but it's not obvious. Anyway, so what I'm saying here is that what I wanted to say here is that in this meetup we have gone through all this book and through this chapter as well, and this, you know, every time you go through it, you think you have convinced yourself of something, and then you read it again. It's just very, very difficult.
So
yeah.
I have a question about actually this section right here, ends as equalizers. I'm sorry, were you done with what you were saying?
Absolutely.
Okay. Yeah. You know, he basically says, okay, here's lambda, here's rho, and then we can define this type prod P of P, which is then for all AB, that thing. But that doesn't look, and then he says, okay, you can express lambda and rho in terms of that. But is that really right? Because like lambda, the A, you know, the A that's PAA is the same A as A to B and PAB. And, you know, whereas that for all is, you know, has bound A and B. So it would be more like PAA arrow for all CD, you know, and it would have no connection to A. So what am I missing here? Do you know what I'm saying?
Not sure. So first, let me just point out one thing, which when you write type prod P equals for all, right? This for all on the right hand side is actually the existential quantifier.
Okay.
I think that's.
Well, it is a for all if you think of those as arrows, but yeah, if you were to kind of, it would be exists AB. If you put the parens around exists AB and then A arrow B to PAB, I think, yeah, it would be an exists, but.
Right. So because if it were, because if for all AB, A to B, PAB would be just A and B on the left in Haskell. So if you had a
A and B
universal
on the left.
quantifier, yeah,
Okay.
if you had a universal quantifier for A and B, you would have just written type prod P, P, A, B on the left equals that. So in Haskell, for all is on the right is existential, and on the left it is universal.
So, I mean,
When
when I
you
think of
define a
for
type,
alls, I think of, basically their functions, right? If we look at them in a dependent language, they're just
yeah,
functions from type, A, B are types, arrow,
yeah,
but it's an arrow. It's not a tuple. But if you query it, it becomes a tuple.
mm,
But anyway, the point is whether it's an exists or it's a for all, A and B get bound in that thing, right? And
yeah.
so if you then say lambda is a profunctor takes a PAA to this thing that doesn't have a free in it anymore, it doesn't seem like it would be equivalent.
Hmm. Prod P. Hmm.
This is what's confusing to me. You said, Sergey, you said that the for all on the type prod P definition
Yeah,
actually means existence, right?
yeah, I
So
think so.
that means in the definition of lambda, is there an implicit for the logical for all there,
Yeah,
right? For
Yeah.
all A, B,
Yeah.
PAA arrow, and then the type should be there exists A, B, A arrow B. Is that correct?
the type of what should be that.
In the definition of type prod P,
Oh, I
the for
believe,
all
yeah,
is actually exists, right? From
Well, I
our
think it,
logical sense, even though Haskell uses for all, you're saying it actually means exists. A B.
well, that's what I remember from my readings about Haskell, that
Yeah.
when you define a data type, when you write for all on the right-hand side of an equals,
Yeah.
it creates an existential quantifier. But
Okay.
I'm confused as to what is going on in this section. So why do you lambda profunctor P diaprod, which is diagonal product of all PAA.
so that's just the plain product without
Just a
any
plain,
constraints.
just plain product of all PAAs into something that makes no sense to me. Yeah, I don't know. So
Yeah.
to me, this is lambda P is lambda on PAA. I don't understand why you're allowed to apply lambda to a for all A PAA. And
I mean,
I don't know.
yeah,
So,
his
but
notation is confusing because PAA there is one of those for all things, whereas the PAA that he used up in the lambda definition is the value of the cell PAA.
right.
It's a value of that thing, whereas down here, it's a value of the for all, which
Yes,
is the
yes.
product of all PAAs.
Right. So you
So
cannot
you
apply
can't just
lambda
apply
to
it
that.
to PAA and say, okay, that's the same PAA as up
You
there.
cannot.
It's not.
So yeah, you cannot apply lambda to a product of all PAAs. You're allowed to apply lambda to one of them,
Right.
but not to all of them at once.
So maybe there's an implicit
There is
application of the for all to A, and that gives you the PAA. But
yeah, but what
I
is
don't
A?
know.
What is A? Which A?
Yeah. Where did that come from?
Where does A come from? So I don't. Yeah, I just don't understand this.
Hmm.
equalizer of these functions. And yeah, I would be much happier if this were written not in Haskell, but in some type notation that makes for all and exists more clear.
Right, right.
No, this is murky. I cannot. I don't think I ever understood this.
This
Here's
probably,
okay.
Oh, and
probably
there's
won't make you
and is
happy here, but-
equalizer.
Sorry, Hugh.
This may not make you happier, but in NLab, they do talk about ends as equalizers. Yeah.
Of. Oh my God, what does that mean?
Mm-hmm.
It's an equalizer of.
Wait, so first we're talking about limits.
Yeah.
Talking about a limit as an equalizer? Wow, I don't think I've ever seen that.
Oh, huh.
Here we are staring at this.
Yeah.
Yeah.
What's okay? So what's their pi notation? That's like a for all, or is
Yeah.
Infinite
Alright.
product.
Yeah. What is S and what is T?
Yeah. Where is S and T? And what is P here? Is that defined
Mhm.
elsewhere?
Oh, this is just
Or is that a projection? Is P the projection?
no, projections must be lowercase pi usually.
Okay.
In this
That's the
business,
law.
projections are lowercase pi's at least.
Okay,
but
yeah,
any-
I don't understand this at all. I'm
in
gonna,
any ca-
with your
the-
permission, I'm gonna scroll down a little and see where they're trying to go
Sure.
from.
yeah, okay.
Well, we should have defined all these things. What this is?
Okay, so what they're trying to do is generalize the end to enriched categories. And they want to take a definition of end which allows them to do that. And that's why they're using equalizers.
Mhm.
Oh, look, it's lambda and rho again. Must be where Milevsky got him.
Uh-huh.
So over.
What is PR? Projection of something?
Must be.
Okay, so this is probably where
That thing
he got it
after.
from. But this is completely unclear. So,
Okay, I'm getting lost here. I can try to prepare this for next time if you like.
Yeah.
I'm gonna move on if that's okay.
yeah.
And, okay, so in an enriched category, you define n to be the corresponding equalizer.
We're it's equalizer. So is that's so is that first arrow supposed to be more like an isomorphism? Because you're sort of saying that the end is like the equalizer.
Oh, okay, so that kind of makes sense. So this is right. So when you produce an end, it should be a map from some integrally thing of these endomorphism objects to
Just
Oh,
the product.
to the product. So you want it to be, roughly speaking, a subset of the product. So here's the big
Exactly.
product, right?
Yep.
And
Yep.
here's this thing, which is going to wind up being the subset of it. And which
Mhm.
subset is it? It's the one precisely that equalizes this row and this lambda.
Uh-huh.
Okay, so that kind of makes sense.
Oh, okay.
Hmm, hell is an adjunct? Is it like an adjoint?
In equation 1, in the right-hand side, square brackets indicates what? The functor category from C,
Yeah.
C1, C2 into F, C1, C2.
Yeah, that sounds right.
Okay. And so C is already a V enriched category, but then what does C left paren C1, C2 mean? Those
That's
are
the
the
Hom
arrows.
set.
Yeah, it's the Hom set, which lives in V.
V. Ah, okay. And then F maps into V. Okay, got it.
Then F. Oh, okay. C is
Also-
just the Hom. Okay, but F is something else, right? F is a
Right. F is a functor
functor.
that whose target is V, but C is a V enriched category, and therefore all the Hom sets are also in V. Okay.
Right.
Is that right? Is that what it means? Okay.
So the Hom functor of C has the same shape as F.
Yes.
They're the same. They have the same type. Those two things.
Right. That's right. Okay.
So that's why you can line them up next to each other, and that should make sense.
And the square brackets here just means then arrows in V.
Yes, I
Okay.
think that's right.
Okay. I see. So for all combinations C1 and C2, wow.
Hmm.
Mhm. Mhm. Where'd that go?
This is my common experience. I look at something and then it's like a fog. And then I have to come back to it, and I have to come back to it and come back to it. And then at some point, it's like, aha. But I have still a long ways from that for the ends.
Yeah. Well, remember, there was a time when just thinking about a functor made your head hurt,
Yes.
right?
Mm, mhm.
So,
In the functor category.
yeah.
Yeah.
So we do, yeah, it does sink in gradually over time. I still don't understand how this rho and this lambda are being defined, though.
They're being defined as the adjunct of another functor.
What is it? Like, is that the same as an adjoint?
Yes, I think so.
Hmm.
So I'm sort of comparing this a little bit to Maluski's definition. Then the rightmost pi, I think, maybe corresponds to his prod P, which was the for all AB, A arrow B to PAB. And that's sort of the same form because, right, we're saying that that thing that you're pointing at, yeah, that's an arrow from C1 to C2, right? That's your arrow. And then the square brackets means that it's an arrow from the arrow to the value of the functor, something like that.
In Milievsky, the lowercase p is the same as the uppercase F that we're seeing here.
Right. And A would be C1 and B would be C2.
Yeah, okay. Adjunct.
I think.
Why?
But then, yeah.
I think I need to draw that. If this is an adjoint to that, I think I need to draw the diagram, draw like little pictures of what the relevant categories are.
So are rho and lambda here natural transformations? Are these things functors that they're operating on? Oh,
They must.
They must be
No.
functors because we're in V.
They're-
All of this is in V, right? F of C1 is an object in
in V, so
V.
it's just a
So is-
regular arrow.
So is this. Oh, you're right. Okay, sorry.
but is V is an enriched functor? So does that mean all the values of V are functors?
No, sorry. V is just a category. What they're saying up here is
Okay.
that F is a V enriched functor.
Oh,
So this F,
okay,
think of V as like set. That's probably the easiest.
okay, all right.
Or it's, yeah.
Well, what does it mean to enrich a functor?
Ah, well. You have to start out with what an enriched category
Yeah,
is.
all right. No, let's not. Well,
It's the
yeah.
it's the natural notion of structure preserving map between two V enriched categories, I guess. But I don't.
I think of it as, instead of home being a set, it has more structures.
Yeah.
So the arrows between C1 and C2, instead of just being a set of these arrows, there is a relationship between these arrows, so that, let's say, one is less than another arrow, some kind of ordering relationship, or any other kind of some extra property
There's
between
a
those.
topology on them, or
Right. Like maybe you can add two arrows to produce
Exactly.
another arrow, or there is a metric notion of a size of an arrow, and so on. That's how I think of it, as
Yeah.
that the home set is not a set, but a group or a monoid itself.
and then the
It's a set
functor,
with structure.
Yes.
yes, and the functors have to respect that structure as well.
Ah. Okay.
Somehow.
Yes.
So we're running low on time here.
Oh, you're right.
So
But
so
this is great, though. I mean, I really appreciate taking the time to cover this, because it seems like this is, important stuff. So
cool. Yeah, well, I'm certainly learning some stuff here. I'm trying to shoot. So we're still stuck on page 7 of the original paper. We know a little bit more, but we're in the same place in the original paper.
Does that mean we want to move on to page 8 for next time?
No, maybe we need to go backwards.
Back to page 6.
yes, to make progress, we need to retreat. We need
I
to
think it's
regroup.
fair to say it would be reasonable to continue our effort to understand coends and counata.
Okay.
But so I would be happy to do that, but I'm certainly open to other suggestions as well.
I would like to also just understand the first part of, chapter 2, the optics, with, their general setting there that allows you to use optic of these different things and end up with lenses and monoidal. But anyway, just that first sort of definition of what an optic is, I'm still struggling with. What is a monoidal V functor L and R and stuff like that?
Yeah, from that point of view, it might make sense to look at this, because this whole idea of enrichment is related to, I guess, ends and coends are a thing you often want to use in an enriched category. That's the sense that I get from the end. But Anyway, yes. Yeah, I would still be interested in looking back at those things. And yeah, and Sergey had this way of looking at this thing, right? And just kind of replacing the co-end with an exists.
Mhm.
This
then-
this is the
And magically
Koyoneda.
using Koyoneda, yes, which I need to go back and do that again because it was interesting, but I didn't.
This is
Couldn't think
Yeah.
you show the construction of the co-end, but when we write exists in the programming language, we don't seem to be identifying anything by any kind of equivalence relation. Or maybe we are, but we're not aware of it.
Hmm.
So that's what I would like to understand. Certainly there is a lot of redundancy in this exists. It's a sum over a lot of things, and we're not really interested in that. We don't see what, the whole point of exists from a programmer's point of view is that we don't know what that type is. It's hidden from us.
Mhm.
We know it's there, but we don't know what it is. We cannot get values of that type because we don't know what that type is. So we can use those values, but we don't really know what they are. And so that's the whole point. So there is some kind of quotienting over those all those possible types that we'll never actually see. The simplest example is exists a dot a. So, and that's just a exists value of some type that you don't know what it is. It exists, and in programming, this is equivalent to just a unit value, because there's not you know it exists. You can you can compute it, but you have no information that you can extract from it. So there is a huge quotienting going on here somehow, but it is not explicit in programming. So, and it was explicit in what Hugh was showing. There's a big explicit quotienting of some huge thing. And I would like to see that this is what the programmer is expected to be if you apply this to programming.
Cool. Would it help? I should go, but would it help to like paste that into the Slack or something? That little
Sure.
treatment that I had. I mean, I'm happy to do that if that will help. There's probably a way to do it.
Just do a screenshot and paste it in.
Yeah, I will try to do that.
Thanks.
Okay.
So
Thanks.
let's choose a date for next time. How about the 22nd of January? Is that past everybody's holiday commitments?
Good by me.
Sure.
Okay. All right.
No objections?
Ends and co-ends and Yoneda and co-Yoneda, and finally the paper that we are actually supposed to be reading.
All right.
All right.
Okay.
Thank you.
Till then,
Thank you all.
Bye.
Ciao.
All right.
Happy New Year.
happy New
Yeah.
Year.
Happy New
Merry
Year.
Christmas.
Happy New Year.
Happy
Merry Christmas.
Bye.